All right, let's take a look at another example. So an automobile assembly line operation has a scheduled mean completion time of 13.9 minutes. The population standard deviation of completion times is 1.7 minutes. It is claimed that under new management, the mean completion time has decreased. So they think they are, under this new management, able to complete these cars more quickly, so in less time. To test the claim, they take a random sample of 35 completion times under the new management. The sample mean is 13.6 minutes for these. We'll assume the population is normally distributed and assume the standard deviation under the new management has not changed from that under the previous management. So based on this sample data and at a 5% significance level, can we support the claim that the mean completion time has decreased under new management? All right, so I'm always going to focus on the claim being made first so we can write our hypotheses. So let's start with that. So H naught is the null hypothesis, H1 the alternative hypothesis, and we're going to focus on writing our claim first. And the parameter that we're testing is the mean, so population mean, mu. And they'd like to see if their completion time has decreased, so is smaller. Decreased is smaller than what it had been previously. So previously the mean was 13.9. The new management thinks they got this number to decrease. So when we have a less than case in our alternative, that's what makes this a left tail test. Our null hypothesis will be equality always, because when we start a hypothesis test, we assume that the null is true. So that's why our mu naught is there at the center of the graph. And I'm going to record that here as well. So mu naught is 13.9. All right. So they write their hypotheses and then they go out and get some data to see if they have evidence that they have decreased completion time. So they took a random sample of 35 completion times. So there's our sample size, lowercase n. And the sample mean for those times came out to be 13.6 minutes. 13.6 minutes. Assume the population is normally distributed and assume the standard deviation has not changed. So originally at the top here, they said the standard deviation was 1.7 previously. We're going to assume that that number is still 1.7 for sigma. And we're using a 5% significance level. So there's our alpha. Let me write it in percent first. So alpha is 5% or in decimal 0.05. Okay, so I'm actually going to set up the traditional method first, and then I'll go back and find the test value. So let's talk traditional methods. So we have to find a critical value or values. So for a left tail test, all of that area alpha is going to be on the left side. So for a left tail test, the area left of the critical value will be our alpha. So for a right tail test, alpha was on the right. For a left tail test, alpha will be on the left. Hopefully it'll be pretty logical. So that's 0.05. So to find that z-score, our critical value, because we know the area left of it, we can just go directly to inverse norm and inverse norm that value of alpha. All right, so let's take care of that. We'll inverse norm 0.05. And that comes out to be, so this is the one that has the rounding discrepancy. If we were doing 2 places, it looks like negative 1.64, rounding correctly. But our textbook, when using 2 decimal places, makes that one negative 1.65. So it says that on our table as well, that that's what our textbook will use. So in reality, in the end, it really wouldn't matter here if it was negative 1.65 or negative 1.64. So generally, once we have our critical region, it'll be clear the outcome regardless. So we're just going to stick with that value, 1.65, as we continue here in chapter 8. So just be on the lookout for that one. And I just call it a rounding discrepancy because it's an unusual case here. All right. So let's graph our critical region. So critical value, I'm estimating there. So our critical value, negative 1.65. I'm going to make a note here that this would be the negative of the Z alpha number. So that notation, Z alpha, is the Z-score that puts alpha to the right. And because Z-scores are symmetric with 0 in the center, this would be the opposite of that number. You do not need to use this notation for me. We can just label it CV for critical value, but you may see that on Alex, and I just wanted to explain why they're doing that. So lovely notation, but we'll just say critical value. And then that critical value was based on making this area to the left of it. It's going to continue up here. So that area to the left of it, because it was a left-tail test, is our alpha. So that area, oops, I miswrote right. That area to the left is 5%. Okay, that is the setup for the traditional method. And then we go out and look at where our sample mean falls on that number line. And to determine that, we change it into what we call a test value. So the test value is the Z-score that corresponds to this value of X bar. All right, and because we are doing a claim about a population mean and sigma is known, we can use a Z-test to find that critical value. So you do not have to do a by hand calculation unless you would like to. You can always use technology to find that number. All right, and actually while I'm here in the traditional method, I forgot to label that the Z-scores that make up this alpha region are what we call the critical region. And then the unshaded part of the graph, so those Z-scores make up the non-critical region. All right, and I'll add here, critical region is also called the rejection region. Sorry, there's different names for things. The critical region or rejection region, and then our non-critical region or non-rejection region. All right, so let's find our test value. So I'm going to go to my Z-test. And my mu naught, 13.9. Got my sigma, 1.7. My X bar, 13.6. My N, 35. And then my direction of my test. So the claim here, so mu, and then we want that to be less than 13.9, which is our value for our mu naught. So we want the second choice, mu less than the mu naught value. And I'm going to use calculate again. I'll do draw in a moment, but we're going to go calculate. And that Z-score that you see is your test value. So I'll round to 2 places. So that's negative 1.04. And that tells me on my graph where is 13.6 relative to that center line. All right, so let's graph it. So negative 1.04. So my picture's a little tight here, but that would be maybe there. So test value negative 1.04 tells me that 13.6 is there. So the z-score is negative 1.04. That tells me that my x bar, 13.6, is here in the non-critical region, so the unshaded region. So my test value falls in the, we're just abbreviating everything, NCR, the non-critical region. So if your test value is not in the critical region, it means that it's not far enough to the left to convince me that that value is incorrect for mu naught. So it is smaller, but it's not what we would call significantly smaller. So when our test value is not in the critical region, it means that our decision is do not reject the null hypothesis. And it'll be easy to remember because the not part goes together. If test value not critical, you do not reject the null hypothesis. Okay, so I'm going to do a little reminder up here. So if our decision is don't reject this, so don't reject H naught, that means that we will not support our claim. So that means you don't support the claim because our claim is H1. So when I write the conclusion, we'll address those words. Okay, so our graphing calculator doesn't do the traditional method, meaning that you have to find the critical value on your own using inverse norm. It does not show up when you run a z-test. So your calculator is actually doing the p-value method, and I'll show you the graph in a moment, but we're going to just stick with what we have on the screen right now and draw it first. So for this p-value method, it's a little simpler because it has nothing to do with graphing critical regions. The only thing you graph is your test value. So our test value, negative 1.04, that still tells us that the center is 13.9 and our x bar is there. So it's letting us establish where our sample mean is on this picture. And for a left tail test, the p-value is the area left of the test value. So for right tail test, it was the area right of the test value. So for left tail test, everything's on the left as we graph. So I'm just going to make a note here then that my p-value is the area left of the test value. And I'm just going to draw my line a little bit more straight there. All right, so there's my p-value. Right, so that area to the left is my p-value. And then we're going to see what our visual tells us about the relationship between the p-value area and the alpha area. So I can see here that my p-value area, so up here that will be all of this. We're just trying not to confuse the methods. So that area now is bigger than the alpha area. I can see that. So my p-value is greater than my alpha area. But let's confirm it numerically. So the calculator does the p-value method. So it's going to give you your p-value. And again, it's short for probability value. So that's why I like to write it as a percentage as well. So 14.82%. And that does match my visual because 14.82%, so this area, 14.82% is bigger than alpha was 5%. So the values numerically agree with my visual. So 14.82% is indeed bigger than my alpha. All right. So we have the little rhyme that says when your p-value is low, you let the null go. But my p-value is not lower than my alpha, so we do not let the null go. So when our p-values are big, it means that our x bar is not far out in this tail, and therefore we do not have enough evidence to reject the null. So we do not reject H naught. Okay. So if the traditional method decision was don't reject H naught, the p-value method decision has to also be do not reject H naught. We're just doing the same problem using two different methods. Nobody would ever do both methods except us because we're learning both of them. You would usually pick one method or the other, but they would have to agree in their outcomes for the decision. And what that tells me is that anytime your test value falls in the non-critical region, it guarantees that you're going to have a p-value bigger than your alpha. So these things always go together. Let me write the sentence then. So this was based on a random sample of, so it was 35 completion times. Pushing it in there a little bit. 35 completion times, we conclude, so since we did not reject the null, there is not enough evidence to support the claim that the mean assembly time has decreased under the new management. So they were hoping to bring down the completion time, and their sample mean was somewhat smaller than it had been before, but it's not a big enough difference to convince us that for the whole population of completion times, that the true mean really is less than what it had been before. So we want to see something really small compared to 13.9 to be convinced. Okay. So there's our left tail test. And I am just going to show you on the calculator here. I'm going to go back to my test, my z-test. And the calculator will draw the p-value method picture. So it's shading the p-value. So that's what you're seeing there. And at the bottom of the screen, it gives you your z-score. That's going to be your test value. And it gives you your p-value there that we wrote down. Now, unfortunately, if you try that, there's a potential you're going to get an error. And I can try to make another video to kind of help people fix that problem. But the calculator is capable of drawing